Hello, friends. Welcome to our live broadcast. I'm Alan, and today's live stream focuses on a core topic: the structural design of precast concrete continuous box girder bridges. This type of bridge has become a preferred solution in modern bridge engineering due to its excellent load-bearing capacity and structural efficiency. Our goal today is to explore how to achieve the safety, economy, uh, aesthetics, and efficient construction of such bridges by optimizing spine selection, cross-sectional configuration, pre, uh, pre-stressing tendon arrangement, and support system design. First, let me provide an overview of our company. Our company, Boyoun Heavy Industry, was founded in 2006 and focuses on the research and development, fabrication, marketing, on-site technical services of steel formwork for bridge, viaduct, tunnel engineering. The headquarters and main factory are located in Binzhou City of Shandong, China, with international department located in Beijing. The annual output is more than 75,000 tons. Boyoun has been qualified by ISO QM system since its foundation. More than 30 patents have been approved each year. Boyoun has served over 1,200 infrastructure projects, mainly for high-speed rail, expressway, railway, highway, and other large-scale infrastructure projects with experienced formwork solutions, cooperated with giant state-owned enterprises and well-known overseas construction groups. Over the years, we have gained extensive experience and expertise, expertise and built a strong reputation in the industry. We are dedicated to providing our customers with high-quality products and, more importantly, with excellent service and technical innovation. For general design principles, the the design of precast concrete continuous box girder bridges shall comply with a series of general principles to ensure structural safety, economy, aesthetics, and constructability. These principles form the cornerstone of bridge design and guide the advancement of the entire design process. For safety, the primary principle is to ensure the safety of the bridge structure. During design, various possible load conditions, including tide load, uh, live load, temperature load, with load, wind load, seismic load, and etc., shall be fully considered. Through accurate calculation and analysis, uh, it shall be ensured that the bridge meets the requirements of load-bearing capacity and stability both under normal service conditions and extreme load actions. In addition, the durability of the structure shall be considered, and appreciate anti-corrosion and anti-rust measures shall be adopted to extend the service life of the bridge. For economy, on the premise of ensuring safety, the design shall focus on economy. The project cost shall be reduced through responsible measures such as spine selection, cross-section optimization, and material conservation. At the same time, construction convenience shall also be taken into account to reduce construction difficulty and costs. For aesthetics, as public infrastructure, the aesthetics of bridges is also an important factor and cannot be ignored. During design, attention shall be paid to the coordination between the bridge and the surrounding environment. The techniques such as concise and smooth lines and harmonious color matching shall be adopted to make the bridge a beautiful scenic spot. For constructability, the design shall fully consider the feasibility of construction conditions and construction technologies. A reasonable structural design can not only reduce construction difficulty and improve construction efficiency, but also ensure construction quality. Therefore, full communication with the construction unit shall be conducted during the design process to ensure the implementability of the design scheme. Third, spine and cross-section design. Selection of spine retail. The spine retail is a key parameter in bridge design, which directly affects the mechanical performance and economic benefits of the bridge. The selection of the spine retail shall comprehensively consider factors such as uh, topography, traffic flow, navigation requirements, and construction conditions. Generally speaking, in areas with relatively flat terrain and large traffic flow, the spine rate can be approximately increased to reduce the number of piers and improve driving comfort. While in areas with complex terrain and high navigation requirements, the spine rate shall be approximately reduced to meet the requirements for navigation clearance. The responsible range of the spine rate shall be determined based on specific product conditions through calculation, analysis, and comparison. Cross-section design. Cross-section design is a crucial part for bridge structural design, which is directly related to the load-bearing capacity and the stability of the bridge. The key elements of cross-section design include beam height, top slab thickness, bottom slab thickness, and web thickness. The selection of beam height shall meet the requirements for strength and the stiffness. While considering construction convenience and economy, the top slab thickness shall be sufficient to bear the transmission of the dike pavement layer and vehicle load. The bottom slab thickness shall meet the requirement for uniform distribution of compressive stress. The web thickness shall consider shear transmission and local stability. During design, the recommended range and design method can be provided based on code requirements and calculation analysis results. Fourth, support and support system design. Support setting principles and tab selection supports are important for transmitting components in bridge structures, which connect the bridge superstructure and piers abutments and transmit the loads on the bridge superstructure to the piers uh, or abutment. The setting of supports shall follow the principles of responsible force transmission and clear load path. When selecting the support type, factors such as structural form, load characteristics, temperature changes, and seismic actions shall be comprehensively considered. Common support types include fixed supports, sliding supports, and rolling supports, which shall be selected according to specific conditions during design. Influence of supports on bridge force and stability. The performance of supports directly affects the mechanical performance and the stability of the bridge. Reasonable support setting can reduce the deformation and the displacement of the bridge superstructure and improve the overall stiffness of the structure. While unreasonable support setting may lead to uneven force on the structure, excessive, excessive stress, concentration, and deformation, and even structural damage. Therefore, the influence of supports on bridge force and stability shall be fully considered in support design. Design ideas and methods of support systems. The design of support systems shall follow the overall design principle to ensure the coordination and consistency between supports and the bridge structure. During design, factors such as the arrangement position, quantity, and type of supports, as well as the connection method with piers or abutments and the bridge superstructure shall be considered. At the same time, necessary mechanical analysis and verification of the supports shall be conducted to ensure their safety and the reliability under various working conditions. 5. Arrangement of pre-stressing tendons. Principles and methods of pre-stressing tendon arrangement. The arrangement of pre-stressing tendons is a key link in the design of pre-stressed concrete bridges. Reasonable arrangement of pre-stressing tendons can effectively improve the load-bearing capacity and crack resistance of the bridge. When arranging pre-stressing tendons, the principles of clear force transmission and uniform distribution shall be followed to ensure that the pre-stress can be transmitted to the concrete in accordance with the design requirements. The arrangement forms of pre-stressing tendons include uh, longitudinal pre-stressing tendons, transverse pre-stressing tendons, and vertical pre-stressing tendons. Longitudinal long, longitudinal pre-stressing tendons are mainly used to improve the load-bearing capacity and crack resistance of the bridge superstructure. Transverse pre-stressing tendons are used to improve the transverse stiffness and stability of the structure. Vertical pre-stressing tendons are used to control stress concentration and deformation in local areas. Friction loss and encourage efficiency of pre-stressing tendons during the tensioning process of pre-stressing tendons. They will be affected by various resistance, resulting in friction loss, which will affect the actual tensioning effect and encourage efficiency of the pre-stressing tendons to reduce friction loss and improve anchorage efficiency. Corresponding measures shall be taken during design, such as selecting tensioning equipment with a low friction coefficient, optimizing the arrangement form of pre-stressing tendons, and strengthening the structural treatment of the anchorage zone. 6. Arrangement of uh, diaphragms. Functions of uh, diaphragms is an important transverse connecting components in bridge structures, whose main functions include improving the overall stiffness of the bridge, restricting distortional deformation, and transmitting transverse shear force. Through reasonable arrangement of diaphragms, the integrity and stability of the box girder structure can be effectively enhanced. The load transmission path can be optimized, and the stress concentration can be reduced, thereby improving the load bearing capacity and the durability of the bridge. Arrangement positions of uh, diaphragms as supports. Diaphragms are usually arranged at each support of the box girder to enhance the transverse stiffness of the structure near the support and restrict the generation of distortional stress. For curved box girders, when the inner radius is within a small range, additional diaphragms shall be arranged between spines to further improve the overall performance of the structure. At mid-spine and other necessary positions, in addition to the support positions, diaphragms may also need to be arranged at mid-spine or other necessary positions according to the spine and width of the bridge. The arrangement of these uh, diaphragms shall be determined through detailed structural analysis to ensure the stability and safety of the overall bridge structure. Thickness requirements of diaphragms. The thickness of diaphragms shall meet the force requirements and consider construction convenience and economy. Generally speaking, the thickness of diaphragms as side supports usually ranges from 0.8 meters to 1.2 meters. The thickness of diaphragms at middle supports shall be determined through calculation based on force conditions such as the position of the supports, generally reaching more than 1.2 meter, and shall also meet the requirements of structural details. For prestressed concrete continuous box girder bridges, the thickness of diaphragms shall also consider the arrangement and anchorage requirements of prestressing tendons to ensure that the pre-stress can be effectively transmitted and exerted. In addition, the arrangement of diaphragms shall also consider the coordination and integrity with other structural components. During the design process, coordination with components such as the main girder and the supports shall be conducted to ensure that the entire bridge structure has reasonable force transmission, clear load path, and good stability. Conclusion. In summary, this study conducts a comprehensive and in-depth discussion on the structural design of pre-stressed concrete continuous box girder bridges. Through spine optimization, refined cross-section design, scientific arrangement of pre-stressing tendons, and innovative design of support systems, the load-bearing capacity, durability, and construction efficiency of the bridge are significantly improved. These research results not only enrich the design theory of pre-stressed concrete bridges, but also provide strong support for practical engineering applications, indicating that this technology will play a more important role in the field of bridge construction in the future. Over the years, with our high-quality products and professional services, we have won high recognition and praise from numerous customers, from the pre-product consultation to the after-sales services. We have made our customers feel completely at ease. We have established long-term and stable cooperative relationships with many customers, such as CREC, CRCC, uh, Hyundai, ITD, IGM, and etc. This is not only our honor but also the driving force for our continuous progress. With the continuous advancement and acceleration of China's high-speed rail going global strategy, the in-depth cooperation with Boyoun and uh, internationally renowned enterprises has been continuously expanded, making full use of its own advantages. It actively participates in international and infrastructure construction projects, including the Malaysia MRT project, makes innovative breakthroughs, demonstrates the technical advantages and strengths of Chinese equipment manufacturing enterprises, building the branch of Chinese enterprises, and is recognized and favored by domestic and foreign clients. A large number of major foreign projects have been completed and opened to traffic. Boyoun participated in the construction of projects such as the um, high-speed railway in Indonesia and China-Laos Railway. Boyuan will undertake more model projects recognized by local industry organizations and institutions, promote local economic development, and benefit local people. Our bridge formwork has many significant advantages such as high precision, high stability, and customization. Whether you are facing a bridge construction project in complex terrain or have special requirements for products, we can provide you with tailor-made solutions to meet the needs of various bridge construction projects. If you have relevant business needs, please feel free to contact us at any time. We look forward to working with you. Welcome to stay uh, to our live broadcast. Thank you.